An overview of correlation. What is correlation? Suppose a safety inspector decides to determine if a relationship exists between the number of hours of training for an employee and the number of accidents involving that employee. Or suppose a psychologist wants to know if there is a relationship, there is a connection, there is an association between the number of hours a person sleeps each night and the person's reaction time. How would he or she determine if any of these variables are related together, or in general, if you basically can find a correlation or relation between different variables? This is the topic of correlation. In this section, we're going to study how to describe what type of relationship or association or correlation exists between two quantitative variables, and how to check to see if the correlation is significant or it's not significant. As usual, we begin by some simple definitions. What is a correlation? In general, if someone asks you what a correlation is a relationship between two variables. The data can be represented by the ordered pairs like X and Y. X is independent or explanatory variable, so our variable X has two terminologies, independent or explanatory, and Y is the dependent or response variable. The graph of ordered pairs like X and Y is called a scatter plot. In a scatter plot, the ordered pairs X, Y are graphed as points in a coordinate plane, or XY plane, as you learn in algebra. The independent or explanatory variable X is measured on the horizontal axis, and the dependent or response variable that we usually is associated with Y is measured on the vertical axis. When we are talking about a scatter plot can be used to determine whether a linear correlation exists between two variables. The scatter plots below show several types of correlation between variables. For example, here we have a negative linear correlation between variable X and variable Y. If you take a look at the line connecting these dots together, we have a decreasing line. That's why we have a negative correlation. Well, you might see a positive correlation. So if you look at the line passing through these points, it means that we have a positive linear correlation. The line starts increasing from left to right. Sometimes we can't find a linear correlation. Sometimes there is no correlation. There is no correlation between X and Y. Sometimes you need to collect more information, more data. Some other times we can find nonlinear correlation. As you can see here, you have a curve or parabola connecting these dots together. So the behavior is nonlinear. In our class, we are mainly concerned about linear correlation, constructing a scatter plot. An economist wants to determine if there is a linear relationship exists between a country's gross domestic product, which we abbreviate with GDP, and the carbon dioxide emissions, CO2. They collected some data. The data are shown in the table at the left. This data displays the relationship between two variables x and y, but we want to visualize this by a scatter plot. We want to see if we have any linear correlation between the data. The x values are GDP in trillions of dollars that we denote by x, 1.7, 1.2, 2.5, 2.8, 3.6, and so on. And the y values, which are CO2 emissions, associated to each x value is denoted on the right-hand side column. So if GDP is 1.7 trillions of dollars, the CO2 emissions is 552.6 millions of metric tons. If GDP is 1.2 trillions of dollars, then the CO2 emission is 462.3 millions of metric tons, and so on. Now let's take a look at the scatter plot. The scatter plot is shown on the right-hand side. We can basically use the dots and connect these together. On the vertical axis, we're going to have CO2 emissions. On the horizontal axis, we're going to have X values, which is GDP, in trillions of dollars. The scatter plot can be visualized this way. So the minimum value, as you can see, the X value is 0.8 with the Y value of 253.5. This is the first dot representing this point. And then you can continue the process and use the dot plot and graph these a scatter plot using these dots. From the scatter plot, it appears that there is a positive linear correlation between X and Y. Why is that? If you look at the behavior of these dots, even though we don't have all of these dots in between, but if we imagine a line passing through these lines, it's an increasing line. What is an interpretation here? Reading from left to right, as the gross domestic products increase, the carbon dioxide emission tend to increase as well. So that's the interpretation, that's the analysis behind the scatter plot here. For better visualization, we could collect more data and have a better scatter plot. Constructing a scatter plot. A student conducts a study to determine if there is a linear relationship between the number of hours a student exercises each week and the student's grade point average or GPA. So the data are shown in the table below. We want to display the data in a scatter plot mode and describe the type of correlation. So the hours of exercise is denoted by X, independent variable, 12 hours, 3 hours, 0 hours, no exercise at all, 6 hours, 10 hours, 2 hours, 18, 14, 15, and 5. The GPA of those students who exercises 12 hours is 3.6. 3 hours of exercise, 4. No exercise at all, 3.9. 6 hours exercise, 2.5. 10 hours exercise, 2.4, and so on. So let us take a look at our scatter plot. We want to visualize the data, see if we can find a linear correlation between them. As usual, on the vertical line, we have the Y values. On the horizontal line, we have the X values. So it appears there is no correlation. You see, the dots are going up, down again, up. So we can't find a linear correlation. For this data, for now, we can say that, hey, we can't find any linear correlation between the number of hours of exercise and GPA. You might need to collect more data and analyze this further. Correlation coefficient. Now we're going to delve into more detailed mathematical details, analyzing the data using some formulas. Interpreting correlation using a scatter plot can be subjective. A more precise way to measure the type and the strength of a linear correlation between two variables is to calculate the correlation coefficient. Although a formula for the sample correlation coefficient is given, it's more convenient to use technology to calculate the correlation coefficient. It's much more accurate, much more faster. So for now, we're going to delve into the basic math behind it, and then later on, we're going to show you how to use calculator or software to compute the correlation coefficient. Let us define the formula first. The correlation coefficient is a measure of strength and the direction of a linear relationship between two variables. We denote this by R. The symbol R represents the sample correlation coefficient. A formula for R is given below. R, or the correlation coefficient, is equal to, on the numerator, you're going to multiply x and y's together, add them all, multiply by n, minus, you're going to add all x values, add all y values, multiply these together, and on the denominator, you have the square root of n multiplied by the summation of x squared minus the summation of x to the power 2 multiplied by square root of n times the summation of y squared minus the summation of y to the second power. Please note that again, this is the sample correlation coefficient. N is the number of pairs of data. So now that we introduced this formula, how do we calculate the correlation coefficient? Remember that for the population correlation coefficient, it's denoted by Greek letter rho. So in the homework, in the exam, in the news, if you see rho, rho means that you calculated the population correlation coefficient. The range of correlation coefficient is -1 to 1 inclusive. When x and y have a strong positive linear correlation, R is close to 1. When x and y have a strong negative linear correlation, R is getting closer and closer to -1. When x and y have perfect positive linear correlation or perfect negative linear correlation, R is equal to 1 in the positive form and it's -1 in the negative one. Negative relation. When there is no linear correlation, R is close to 0. It is important to remember that when R is close to 0, it doesn't mean that there is no relationship at all. Just that there is no linear correlation. You might find some nonlinear relation as well. Several examples are shown below to visualize how we analyze a correlation coefficient. For example, for a perfect positive correlation, the dots are lined perfectly. For a strong correlation coefficient, you basically see some noise, but eventually you can visualize the relationship and the line passing through these points. A weak positive correlation, we can still see the trend, we can still see the behavior, but we have much more noise around the regression line. With the same argument, when the lines are decreasing, when the points are decreasing, you can basically see a perfect decreasing line passing through these points. Here we have a perfect negative correlation. If you have some noise, but still can recognize the line easily, you have a strong negative correlation. And of course, if R is close to 0 with negative values, you're going to have more noise. In this case, we don't have any linear correlation, the IQ score and the height. The data doesn't seem to be linearly correlated between X and Y. So let us take a look at one numerical example. But before that, let's take a look at the guidelines. Calculating a correlation coefficient in words and symbols. 1, find the sum of the X values, which is the summation of X. 2, find the sum of Y values, which we denote by sigma Y or summation of Y's. Multiply each X value by its corresponding Y value and find the sum. So we multiply X and Y's and then add them all together. Step 4, square each X value and find the sum. So X multiplied by X and then add them all together. Square each Y value and find the sum, the summation of Y squared. 6, use these 5 sums in previous steps to calculate the correlation coefficient. On the numerator, you're going to multiply n by the summation of x, y's, minus, you're going to multiply the summation of x by the summation of y's. On the denominator, you have the square root of n times the summation of x squared minus the summation of x to power 2. And the second square root is n times the summation of y squared minus the summation of y's to power 2. Let us go back to our example. Here we had the GDP in trillions of dollars and CO2 emission in millions of dollars. What are we going to do? We're going to basically take each x and multiply it by its y. You get xy. You're going to take each x, raise it to the second power. You're going to take each y and raise it to the second power as well. You're going to repeat this process. On the second line, you're going to multiply x and y, which is 554.76. You're going to multiply x by itself, 1.2 times 1.2, which is 1.44. You're going to multiply y by itself, which is 462.3 multiplied by 462.3, which gives you 213,721.23. You're going to just repeat this process for each value. Find the sum of all x values. Find the sum of all y values. Find the sum of all x multiplied by y's. Find the sum of all x squared. And finally, find the sum of all y squared. Then punch everything into the formula. Remember the formula? You have n pairs, which is 10. The first pair, the second pair, the third, the fourth, the fifth, and so on. So as you can see, you have 10 pairs here. And R is the formula for correlation coefficient. We have all the missing information. We just need to punch them into the formula. You have 10 times the summation of x, y's that we calculated here, 16,145.46. You just plug that in here, minus the summation of x times the summation of y's that you calculated here, 24.6, multiplied by 5,263, and divide everything by the square root of n, which is 10, times the summation of x squared. The summation of x squared is 79.68 that you can see just right here, minus the summation of x to power 2. So here you have 24.6 raised to power 2. and the second square root can be calculated as well. Further calculation shows that this number is 0.912 or 91.2%. Remember that 91.2%, very close to 1, suggests a strong positive linear correlation between X and Y. So as the gross domestic product increases, the carbon dioxide emissions tend to increase as well. That's the interpretation of the correlation coefficient to be close to positive 1. We have a strong positive linear correlation. It means that as X values increases, the carbon dioxide emission, which is your Y value, tend to increase as well. Regression lines. After verifying that linear correlation between two variables is significant, the next step is to determine the equation of the line that best models the data. This line is called a regression line, and its equation can be used to predict the value of y for a given value of x. Although many lines can be drawn through a set of points, a regression line is determined by a specific criteria. Consider the scatter plot and the line shown below. For each data point, the data points are points, two of them are here, one is up there, one is up there, one down here, one up there. We define di that represents the difference between the observed y value and the predicted y value. The differences are called the residuals, and it can be positive, negative, or 0. When the points are above the line, like these points, 1, 2 points are above the line, then di, the difference between the observed value and the predicted value, is positive, because the observed value is more than the predicted value. The residuals can be negative as well. So if the points are below the line, the observed y value is smaller than the predicted y value. So the difference between them is going to be negative. And if the observed y value is exactly on the line, it means that it's the same as the predicted y value, then the residuals is equal to 0. Of all possible lines that can be drawn through a set of points, the regression line is the line for which the sum of the squares of all the residuals is minimum. So your regression line must fit into this criteria. Definition. A regression line, also called line of best fit, is the line for which the sum of the squares of the residuals is minimum. As you remember, in algebra, to find equation of the line, you just need 2 points. Then you can write y equals to mx plus b. M is called the slope of the line, and y is the y-intercept. Basically, to write equation of a line in algebra, we just need slope, rate of change, and the y-intercept b. The equation has the form y equals to mx plus b. Recall that the slope of a line is the rate of change, basically the ratio of its rise over run. The y-intercept is the y value of the point at which the line crosses the y-axis at this point. It's the y value when x is equal to 0. When x is equal to 0, your y is, at this point, in this case, 1. For instance, the graph of y equals to 2x plus 1 is shown at the right, and the slope of the line is positive 2, and the y-intercept is 1. In algebra, you use 2 points to determine the equation of a line. In statistics, you use every point in the data to determine the equation of the regression line. The equation of a regression line for an independent variable x and a dependent variable y is y hat equals to mx plus b. Y hat is the predicted y value for a given x value. The slope m and y-intercept b are given by the formula. M is equal to n times the summation of xy minus the summation of x times the summation of y divided by n times sigma x squared minus sigma x to power 2. And b is y bar minus mx bar, which is the average of y values, minus m times the average of x values. So these are y bar and x bar, the formulas that you learned in elementary part of our class. And please note that the graph of regression line always passes through the point x bar and y bar. Let's go over one example. We want to find the equation of the regression line. Find the equation of the regression line for the gross domestic products and the carbon dioxide emissions, the data we saw in the previous example. For each x value, we have a y value. So how do we find the equation of the regression line? First, we need to find the slope of the line. N times sigma xy minus sigma x times sigma y divided by n sigma x squared minus sigma x to power 2. We calculated all of these numbers in example 1. M, or the slope of the line, is a large positive number, 166.90438. Now we're going to find the y-intercept b. To find y-intercept, b is equal to y bar minus m x bar. Y bar is the average of y values, x bar is the average of x values, and m is calculated here. So b is approximately 115.725. We can visualize this line, and as you can see, it passes through the points for example 1, and as you can see, it is an increasing line. As the GDP in trillions of dollars increase, we see that the CO2 emission tend to increase as well. We can write down y hat, or the regression line, as m times x plus b, and make predictions for future values. What's variation about a regression line? In this section, you'll study 2 measures used in correlation and regression: the coefficient of determination and the standard error of estimate. These are used in machine learning as well. You'll also learn how to construct a prediction interval for y using a regression equation and a given value of x. Before studying these concepts, you need to understand the 3 types of variation about a regression line. To find the total variation, the explained variation, and the unexplained variation about a regression line, we need to calculate the total deviation. then the explained deviation, and finally, unexplained deviation. We have formulas for each one of these. These deviations are shown in the figure below. The formula for total deviation is y sub I minus y bar. Explained deviation and also unexplained deviation have their own formulas. Explained deviation is yi hat minus y bar, and unexplained deviation can be calculated as yi minus yi hat. For a regression line, for any point like xi and yi, it might be above the line or it might be below the line. So in this case, we are assuming that it's above the line. We can calculate the residual, which is the difference between these 2 points. In this case, the residual is positive. The unexplained deviation is yi minus yi hat. Yi is the actual y value and yi hat is the predicted y value. Explained deviation is yi hat minus y bar, the difference between the predicted y value and the average y. And the total deviation, which is the difference between the actual yi and y bar, can be calculated as the formula represented here. After calculating the deviations for each data point, xi and yi, we can find the total variation, the explained variation and unexplained variation. Let's go over a few definitions. The total variation about a regression line is the sum of the squares of the differences between the y value of each ordered pair and the mean of y. The total variation can be formulated as the summation of yi minus y bar to the second power. The explained variation is the sum of the squares of the differences between each predicted y value and the mean of y. We can take a look at the formula. Explained variation is the summation of yi hat minus y bar to the second power. And finally, we have the definition for unexplained variation. It is the sum of the squares of the differences between the y value of each ordered pair and each corresponding predicted y value. And we can formulate unexpected variation as the summation of yi minus yi hat raised to the second power. So we introduced 3 different definitions for you. The sum of the unexplained and explained variations is equal to the total variation. Remember that total variation is explained variation plus unexplained variation. Very good. Another definition for you. The coefficient of determination, or R squared, is the ratio of the explained variation to the total variation. We can write it this way. R squared, or the coefficient of determination, is the division between explained variation and total variation. Please note that it's important that you interpret the coefficient of determination correctly. For example, if the correlation coefficient is R equals to 90%, then the coefficient of determination is R squared, to be 90% multiplied by itself, which is 0.81. It means that 81% of the variation in y can be explained by the relationship between x and y. The remaining 19% of the variation is unexplained, and it's due to other factors like lurking variables or sampling error. And finally, the standard error of estimate, which we denote by S sub e. This is the standard deviation of the observed yi values about the predicted y hat value for a given value of x. It's given by S sub e to be square root of the summation of yi minus yi hat to the second power divided by n minus 2. And as you remember, n is the number of pairs of data. We have some guidelines in finding the standard error of estimate, which is the standard deviation of the observed yi values about the predicted y hat value. And we denote this by S sub e. First of all, make a table that includes the 5-column xi, yi, yi hat, and yi minus yi hat. And in the last column, calculate yi minus yi hat to the second power. Use the regression equation to basically calculate yi hat, which is mxi plus b. And the next step, calculate the sum of the squares of the difference between the y value, which is your yi minus the predicted y value, and raise it to the second power. After calculating the difference, make sure to raise it to the second and add them all together. And finally, find the standard error of the estimate, which is the square root of the calculation, which we done in step 3, goes on the numerator, and on the denominator, you have n minus 2. One quick example for you, finding the standard error of estimate. Let us go back to the GDP and CO2 emissions data. Our goal is to find the standard error of estimate. Remember that we calculated y hat to be mx plus b. You want to find the standard error of estimate. So manually, we want to use a table to calculate the sum of the squared difference of each observed y value and the corresponding predicted y value. Each xi and yi we introduced in the example with some of the calculations. So let me show you. Here you have xi, then you have yi corresponding to xi. In the next step, we calculate yi hat by plugging each x value into the formula to calculate yi hat. And then we find the difference between yi and yi hat. And then we raise it to the second power, take each number, raise it to the second power. And finally, we're just going to add all of these numbers together. This gives you the summation of yi minus yi hat to the second power, which in this case is a large number. Now, when n is equal to 10, and the summation of yi minus yi hat to the second is 108, 563, the standard error of estimate can be calculated as square root of the quantity that you calculated here divided by square root of n minus 2. You can separate these two, or you can put all of these inside the square root, and this number is about 116.492. What's the meaning of this number? Is that the standard error estimate of the carbon dioxide emissions for a specific gross domestic product is about 116.492 million metric tons.